Logical algorithm. The logical algorithm, well, logical means it makes sense according to the rules of logic, some of which I hope you learned in geometry. Algorithm is a method or series of steps designed to produce a specific outcome or solve a specific mathematical or logical problem. Logical algorithm, a solution that makes sense. You may or may not agree with this in a few minutes. I'll give you a quick bit of backstory on the logarithm and why it's impressive and going to be difficult. Bear with me. There was a Scotsman in the late 1500s named John Napier. John Napier was a bit of a loon. He was rich, he was brilliant, he had crazy ideas for war machines that were based on things like Da Vinci's flying machine designs. He was way ahead of his time. He's a bit of what you might call a futurist. Someone who's really thinking way ahead of what his society can implement. The engineering wasn't up there for his ideas for war machines.
Da Vinci invented the tank.
Pardon?
Da Vinci invented the tank as well.
Yeah, and Napier was a similar thinker. My favorite of his clever problem-solving ideas that he actually used in real life was he got his neighbor's pigeons drunk. The reason he got his neighbor's pigeons drunk is his neighbor kept domestic pigeons which flew home to the coop every night, but in the meantime they were eating the seeds from Napier's field. And this is the late 1500s in Scotland. This was not a garden of petunias or something. This was his vegetable source. This was his Whole Foods market. This was his only source of these things. He was quite upset about this, so he went to confront the neighbor. And the neighbor said, "It's not my pigeons, you can't prove it. Besides, they were here all day. And anyway, they were insane at the time." He just said no, basically took no responsibility for this. So Napier, and I think this is incredibly clever, took his seeds the next time he planted and soaked them first in grain alcohol, which apparently doesn't hurt the seed. Planted the seeds, pigeons came by, ate the seeds, pigeons passed out drunk. The neighbor from down the road came up to Napier and said, "I know you did something with my pigeons, even though they never hurt your seed in your garden. I know you did something. You're the reason my pigeons didn't come home last night." Napier said, "Oh, your pigeons that never eat out of my fields? They're sleeping off their hangovers in my back 40. Why don't you go scoop them up?" So he got his neighbor's pigeons drunk to prove to the neighbor that the pigeons were the problem. This is not a normal man. Anyway, he woke up one morning asking himself, what if exponents worked backwards? And the reason why he asked himself this is because exponents should have an inverse, he felt. Now, inverse, we learned for inverse functions, was when you switch the x and the y. But when you switch the x and the y when you were switching inverse functions, you might have noticed that oftentimes multiplication became division because they're inverse operations. Where there was addition, you should have noticed the inverse would often have subtraction because addition and subtractions are inverses. So it doesn't make sense that exponents, which are also in the order of operations, did not have an inverse. Here's one of the last crazy thing I'll say about Napier before getting into the math. Every other mathematical idea, all the way back to multiplication, you can find a progression of work that led to an idea. Einstein credited other physicists with his work with helping him set up relativity. Thank you. Isaac Newton said, "If I have seen farther than others, it is because I have stood upon the shoulders of giants," referring to the work of the mathematicians who came before him. No one can find any evidence that anyone before Napier said, what if exponents work backwards? He apparently thought of it as completely originally as we can know anything to be original from back then. Nothing is written down about it, and that's just possibly unique in the history of math and science thought. Yes?
Do they not have no life whatsoever to be thinking about this stuff?
You're a Scottish lord. You can watch your sheep or do math. There is no MTV. There is no Game Boy. What are you going to do with yourself? Logical algorithm.
Well, he's a lord. He probably has the ability to get rid of
I don't think he necessarily skimmed through that area. But he still had plenty of time left over to think about this stuff. Okay, here's how he rearranged. We'll talk more about the significance of this later, but here's how he inverted exponents. And we'll start with the expressions. I won't lie, the purpose of this won't make a whole lot of sense until maybe Monday. Okay, where we'll get to some ideas on why this was so useful historically. But just to get used to manipulating them, if I have a statement 5 cubed equals 125, the notation Napier came up with to support his logarithms, he rearranged this. He didn't want the answer to be what you got when you raise something to the power. He wanted the answer to be the exponent. So when you rearrange this, he wrote it as log, short for logarithm, base 5. The term base applies to both the base of the exponent, as you already know, and the small number written here, of 125. The logarithm base 5 of 125 equals, and the question this is meant to ask is 5 raised to what power equals 125? So the answer is 3. So when you're looking at a logarithm, the question it's asking is, given this base, what is the exponent that I raise this base to get the number here? That's his rearranging of exponents. It doesn't seem to have a point yet, but we're getting there. Okay, a couple of other logarithm rearranged. What is 2 to the 5th?
128.
What's 2? Almost.
32.
32. Thank you.
Log
2
base
times
5.
2. So what's the log of this one? How do I write this? Log base. What's the base? 2. So that goes from the biggest number to the little number over there.
32 equals 5.
Yep. Log base 2 of 32 equals 5. Okay? Now this isn't that hard, but it also at this point probably seems a little pointless. Actually, I mean, writing it this way seems to work perfectly well for the first 10 and a half years of your education. Why suddenly write it this way? May not fully answer that to your satisfaction for a couple days, but bear with me. A couple other ways this is used. Whoops, let me start with the exponent.
Using a square root.
Pardon?
Using a square root.
Oh, it gets so much use in square roots and cube roots. That'll be Thursday, we'll talk more about that, or Friday. One of the two. Okay, what's 10 cubed? 1,000. 10 times 10 times 10 is 1,000. Rearrange this one for me.
Log base 10 equals 3.
Log base 10 equals 3. Log base 10 of what?
Oh, 1,000.
1,000. I'm going to write this one a little bit differently. I'm going to leave out the base 10. Because if you don't see a 10 there, the assumption is the base is 10. The assumption is that the base is 10. If you see nothing there, you're looking at log base 10. There's a reason for that we'll go into a little bit later.
That is straight memorization.
Pardon?
That is straight memorization. Like if you log 32 equals 5, you're just like, oh, it's 2 because 5 is square, or 2 to the 5, 2 to the 5th is 32.
No, good point, good point. If you don't see anything there, you see, originally they didn't have calculators that could figure these out. And logarithms were very useful in calculations. They became so useful in calculations, for a reason I'll go into tomorrow and Friday, that they actually, I mean, having a sheet of logarithms became like having a TI-83 calculator back then. It sped up your calculations so fast. But you could only have a sheet of one base. And they originally picked base 10. So the assumption was log, if you don't see anything, it's 10. So that's the question being asked. So if you see this question on a test, what is the log, and you don't see a base, of 100? You're supposed to ask yourself, 10 raised to what power gets me 100? And what would that answer be? 2. So if you don't see anything, it's 10. If you see something, it's a different base, and you got to ask yourself a different question. Now there's one other logarithm that gets treated differently. And that is, I don't know, a good question for this. Okay, so I'm not going to present it as one. If you have a logarithm base e of anything, if you have a logarithm where the base is e is a very special number in this case, as I pointed out before, a logarithm